What if I tell you you can do object detection, instance segmentation, panoptic segmentation, keypoint detection in just a matter of minutes without requiring any sophisticated hardware resources? Sounds interesting, right? We will see how to do this using Detectron2 library by Facebook AI Research. So let's begin. So this is the official GitHub page of the Detectron2 project, which is a library that provides state-of-the-art detection and segmentation algorithms, and this is produced by Facebook AI Research, and it supports a number of existing computer vision research projects and applications in Facebook. It also supports panoptic segmentation, dense pose, which is pose estimation, and many other state-of-the-art algorithms. And not just that, it can be used as a library to build upcoming research projects on top of it. And if you check out the blog post, we can see here that this is a modular design that allows users to plug custom module implementations into almost any part of the object detection system, which means that you can create new research projects in just few lines of code. So it is very important for us to know about this library, and that's what we will see in this video. To get started, let's check out a very nice Google Colab notebook, and also let's open the documentation side by side. For those who are new to Google Colab, this is a cloud-based GPU service provided by Google, and this Colab tutorial is the official Colab tutorial of Detectron2, where it consists of two parts. It first shows how we can run inference on images or videos using existing Detectron2 model for instance segmentation, object detection, panoptic segmentation, and many more. And secondly, it also shows how we can train a Detectron2 model on our new custom dataset. So for those who are new to this interface, this is a Jupyter based interface, and each box here corresponds to a code cell where we can enter our Python commands. And to run each cell, we can either press this play button or press Ctrl Enter or Shift Enter on our keyboard. Click on the run anyway. So here we can see that it is allocating the GPU for us, and once it is allocated, it will show a green mark here. So we are connected, and in this cell we install Detectron2. So let me come back when this is done. So we have executed this cell. We can see that green tick mark here. If we go down, we have installed the required libraries, and then we need to restart runtime by clicking on this button and restart runtime, press OK. So we are initializing again, restarting again, and this has been allotted. So this is done. So next is, let's import the required libraries. So this is Detectron2, and these are the Detectron2 utilities. We will see about these utilities one by one in the coming code cell. So let's run this cell. So this is done. Now, as I had mentioned, let's see how we can run a pre-trained Detectron2 model on a sample image. And specifically, we will first see how we can run instance segmentation model based on mask RCNN on a sample image. So first, let's download a sample image onto this server. So we use Coco dataset sample image, and then use OpenCV library to read this image and then plot it. So let's run this. So this is the image onto which we will do instance segmentation. Now let's come to the main part. So to run instance segmentation using pre-trained models, we need to create a configuration file, and then we pass this configuration file to a default predictor to run inference onto this image. Let's see this in more detail. So we use getConfig file method from Model Zoo API. So if you just hover onto this Model Zoo, we can see the documentation. This is the API which contains a number of functions to create common model architecture listed in Model Zoo. You can also check this in the documentation. So if you check the API documentation, you can see model zoo. So this is the same thing which we saw. So what is model zoo? To understand model zoo, let's go back to the GitHub page, and if we go down, we see this model zoo, and if we open this, we can see here we can see the list of models with which this pipelines, this object detection, instance segmentation algorithms are trained. This contains a list of baseline and the number of models with which it is trained and the accuracies. So for object detection, they have trained this many architectures or backbones. For instance segmentation, they have used this many backbones and so on. So each model has a config file. So here let's first do instance segmentation using mask RCNN, which is based on each of pyramidal network backbone. And to do that, we use config from model zoo, and it creates a configuration. So basically, so this is a modular design. So basically, all the configuration information is stored in this YAML format. And to use a different model, we have to just replace the YAML format, the path to the YAML file. For example, we want to use, so right now we are using R50 FPN, which is this backbone, which has this accuracy. But if we want to use a different backbone, we have this model, and to get the path of the YAML file, we have to go to this GitHub page and click on configs, and for instance segmentation, we can pick the appropriate config file. So for example, let me go back to model zoo. So let's say we want R50C4, so we can pick the appropriate YAML file from here and pass it to this get config function. So that's it. This is how we create a configuration, and then we can set the hyperparameters. So this is the score threshold at test time, and then we have to load the weights from the pre-trained model. For that we use get checkpoint URL. So this is also one of the method from model zoo API. So it returns the URL of the model trained using the given config. Once we have the configuration, we pass the configuration to a default predictor. So what is default predictor? Default predictor is it creates a simple end-to-end predictor with the given configuration, and it runs on a single device for a single input image. So basically, we create this default predictor, and then we pass the image to the default predictor, gives us the output. So let me explain it more. So let's first run this cell. So first it will download the pre-trained model, as we can see here, and then run the inference using this model. So this predictor gives us output. So let's see what this output exactly means. So to know that, we can go back to the documentation. They have also given the link here. So this is the same documentation of Detectron2. So here we can see the output format of the model. So for each image, we get a list of dictionary. So it outputs one dictionary for each image, where the dictionary consists of following fields. So depending on the task, it outputs the appropriate fields. Since we are doing instance segmentation, we get instances field, which consist of another subfields, which are predicted bounding boxes, scores, predicted classes, and so on. If you are doing keypoint detection, then it also outputs these keypoint predictions. So this is the output format, and depending on the task, you can check out the appropriate output format. So basically, we can use this documentation to know more about it. So this is just looks at some of the outputs, and then we have the output now. This output onto the image. to do that, we have a visualizer API. So it draws the predictions, output predictions onto the image. So we create a visualizer object by passing the image and the metadata of the dataset. So metadata is basically contains the information about the dataset, means what are the which kind of key points, so what kind of key points, what are the number of classes, what are the class names, and so on. So we create a object and then we call draw instance predictions method from this visualizer API, which draws instance output predictions onto the image. So you can also see the documentation in, you can also read the description of this method into the in the documentation. So we have the output image and we plot it using the IM show. So that's it. So we have applied instance segmentation, mask or CNN based instance segmentation model onto this image. Let's also see how you can do object detection, panoptic segmentation, etc. So to do that, we just need to update the configuration. So let's make a copy of this here. So let's say we want to do object detection. So to do that, we go to the model zoo and pick the model as per our choice. And this is the object detection baselines trained using Coco dataset. And let's say we want to pick this model which have these accuracies. So this is R101C4. So to get the location of the YAML file, let's go to the configs from the GitHub page, and let's now go to the detection, and we want to pick this R101C4. So we can see here that this is the YAML file. So let's copy this file name and paste it here. So we have the YAML file and this is detection. Similarly, we have to copy the same thing here. So that's it. We have created the configuration for the object detection using faster RCNN, which is based on this backbone. So it creates the configuration, loads the pre-trained weights, creates a predictor using this configuration, and then applies the predictor onto this image. That's it. It's as simple as that. So as expected, it will first download the pre-trained model and then run the prediction. And we have the outputs. Now let's also visualize the outputs. So let's make a copy of this so that we can compare the outputs. So we have the same visualizer, then we draw the instance predictions using the new outputs. So this output will contain the appropriate items depending on the task. So we don't need to worry about it. This draw instance method takes care of the things automatically. So this is the output we get. So this is the task of object detection where we just want to obtain bounding boxes around each object. So that's it. We have used famous faster RCNN algorithm onto the image. This is object detection. Similarly, we can also do panoptic segmentation. Semantic segmentation, and many more. I hope you must have got the idea. So basically, we have to choose the model from the model zoo and pick the appropriate config file from here and then use it and create a configuration and load the model weights, create a predictor and apply it onto the image. So that's it. This is the pipeline. So assuming this part is clear, let's go to the second part, which is how we can train it on a custom dataset. So this is a very interesting part. So we can even train on our custom dataset using Detectron2 for all these tasks. So that's the beauty of this. As an example, they have used a balloon segmentation dataset. For that, we need to download it first onto Google Colab server. So this is a very small dataset and we are done with the downloading. So for any new dataset, we need to register this dataset to Detectron2. So what do we mean by that is we need to create a data loading function which outputs the information about the dataset in a format which can be used by the training, inference, and all the further pipelines in Detectron2. So to do that, let's check out this function here, which gives a very clear picture of how to do that. So first thing is we need to register your dataset, which basically tells Detectron2 how to obtain the dataset, and optionally we can also register metadata which can be used by the visualizer. So this is not compulsory but recommended. So to register a dataset, there are two things. First, we need to create a function which returns a list of dictionary in the format below, which we will see. Once we have this function, we call register method from the dataset catalog API, which takes two arguments. The first is the name of the dataset, and the second is the function which we have just created. And then to get the sample image from this dataset, we call the get method from the dataset catalog API. So the main part is we need to define the dataset function accordingly based on the annotation format of our custom dataset. So basically the function which we will write should output the dictionary which contains following fields. So depending on the task, we need to write the function accordingly. So these are the common fields which we must output for all the tasks. And if you want to do instance segmentation, we also need to give this field which is annotation. And to know more about annotation, we can go down, and this is basically a list of dictionary which contains subfields as shown here. So that is what we will do. We create a get balloon dictionary function which loads the annotation which is present in JSON format in this dataset, and then extract the important information for each image such as file name, height, width, and the annotations, and make a dictionary containing fields which are required by the Detectron2 which we have seen here, and then create a list. So that's it. So this is where we have to show our coding skills and write this function appropriately based on the annotations of our custom dataset. So once it is done, the almost 90% task is done, and we register it using the dataset catalog API and then also the metadata. So here if you see, this is nothing but, you can say this is this. So basically we register the dataset by providing two arguments, which is the name of the dataset, and in this lambda function what we are doing is basically this. So here they have, this is a concise way of writing the code, but basically we are doing this. So we call the register method of dataset catalog API and pass the name of the dataset and the function which we have just created. So that's it. So that's it. Let's run this cell. So this is executed, and then we can visualize some of the outputs. So we call the function which we have created, which gives us the dictionary of data, and then we sample some of the items from this dictionary. So let's say we sample just one item, and then we use OpenCV to read the image and call visualizer. We initialize visualizer using the image and the metadata. So this Boolean metadata is very simple. If you just see, this contains the name of the dataset and the number of classes. So this is it, and we call draw dataset dictionary method of visualizer to draw the dataset annotations onto this image, and we can, so this is one of the image. So every time you run this cell, you will get different image because we are doing random sampling. So this is just a sample image which is plotted. So then is the training part. So to train it, it's very simple. We use the default trainer API, which is a trainer with default training logic, and it does the following things, which we can see here. So basically, we need to create a configuration file, and we do the same process. So we define the YAML file for the appropriate model with which we want to train or fine tune, and then these are the number of these are some hyperparameters like number of workers, and we this is important. So we load the weights using a pre-trained model, and then we say how many batches, how many iterations, how many steps, and other parameters we set here. And this configuration is then given to default trainer, which basically creates a trainer with which we can train our model. So once we have this trainer, we just say default trainer dot train. So this will train it. This will train our new data set, and this will train the instance segmentation model using our new data set. So let's run this. So you can see this is the model, and it has started the training. We can see the loss here. So let me pause this video and come back once it is done. Okay, so now that the training is completed, we can see that the loss has reduced and all the losses have reduced. Now we can also visualize this on tensor board. So we can see here that all the losses start CNN loss, this is accuracy, this is the classification accuracy, are the loss functions. So we can see all the loss curves here, and then let's finally do the inference using this fine-tuned model. So to do that, we just need one change, that we need to update the weights with our newly created trained model. So that's it, and then we can update the threshold to 0.7, or we can keep it same as 0.5, and then we call the default predictor using we create a default predictor using this configuration, which gives us a predictor which can then be used on all the images. So let's create the predictor, and then uh, here what we are doing is we are running the predictor, we are applying the predictor on all the images in this dataset. So we create a visualizer. So we apply predictor onto this image, which gives us output, and then we use visualizer to plot the outputs onto the image. So this gives us the outputs. So if we see, we can see that it has perfectly located the balloons in this dataset. So it's pretty good. So now Detectron2 has also APIs for evaluations. So we can run this evaluation script, which gives us the average precision accuracies for all the thresholds. So you can learn more about it from the documentation. So yeah, finally they have also shown how we can use other type of built-in models, which we have already seen. So this is the key point detection. So here we can see all the key points of the person are detected, and similarly we can do panoptic segmentation. So this is one kind of output, and we can also apply it on a video. So I will not run this cell because it will take some time to download this video, but I guess you must have got the idea by now how to use this dataset and how to use the documentation and these config files to do the inference as well as do the training. So this is all. I hope you got to learn a lot of things, and I hope you can use this in your own projects. And yeah, that's all for this. See you soon in the next video. Thank you very much.